Okay, so thanks very much for coming to the Doherty Institute. Welcome to our symposium this evening, You Never Forget the Flu, and thanks so much for braving the Antarctic weather to join us, all of you. I'm Dr. Mike Catton. I'm one of the two deputy directors of the Institute, and I'm director of the Public Health Virology Lab that is housed here. I've got a couple of housekeeping arrangements to take you through first. Firstly, I'd like to take time out to acknowledge the traditional owners of the land on which we're meeting, so the Wurundjeri people of the Kulin Nation, elders past and present, and any Indigenous people who may be with us this evening. Secondly, in case of emergency, there are assigned exits here at the front and up at the back. Up at the back also are bathrooms at the back and on your left. We're, as you may have noticed, being filmed this evening, mainly concentrating on the speakers, but if anyone has any concerns about that, please feel free to talk to one of the event organisers. And lastly, feel free to talk on social media as we progress using the hashtag #FightTheFlu. So, no dots, no gaps. So, flu. It's a word, well, you've probably seen flu in the media already this season, or public health announcements about flu and vaccine. Flu's a word we bandy around. I've had the flu, I've got the flu. Usually we mean I've got a cold, it just sounds more dramatic. We're normally talking about a few days of runny nose or sore throat and coughing and sneezing, but you never forget the flu, which is a much more severe, longer course of disease, severe and potentially fatal. And you'll hear more about that from the speakers that we've assembled to share their experiences and expertise with you this evening. So we have 3 influenza experts, and we have one person that has recently experienced flu firsthand to talk to you with their experiences and expertise about flu, the clinical disease, both from a technical perspective and from first-hand perspective, as well as the importance of annual vaccination and of exciting research toward goals like new medicines and new vaccines. So flu's a really interesting virus, never a dull moment with flu, and it's a really important program for us here at Doherty. Across a range of activities that include surveillance and epidemiology, diagnostics, characterising new strains that might go into vaccines, and investigator-led research. So, in close collaboration with our partners, including the Department of Human Services Victoria, our co-hosts this evening, as well as the Commonwealth Government and the World Health Organisation. So, without further ado, I'd like to introduce our first speaker, which is Dr. Angie Bone, Acting Chief Health Officer of Victoria from the Victorian Department of Human Services. Dr. Bone's a really experienced public health physician, long experience and expertise in environmental hazards and in infectious diseases, has a personal interest in environmental determinants and sociological determinants of health, including climate change, housing, urban planning, and of course infectious diseases. So Dr. Bone is a Fellow of the Faculty of Public Health in the UK and an infectious diseases physician, has long experience in health protection, and I'd like to invite her to the stage to share her experiences and expertise with us. So Dr. Bone.
Thank you. Okay, can I grab that? Yeah. Thank you. Okay, thank you very much. I'm very pleased to be here today. I should say that, yes, I'm from England and I've only been in Australia for about a year, so I'm still trying to adapt to winter being during summer and things like that, but it was very nice to see the weather today because it did make me feel at home. Before I go into my talk, we thought it would be helpful to just show you a video of some people talking about their experience of the flu. So I'm going to show that first and then talk a little bit more about what the flu is, how it makes you feel, what we're trying to do about it. So I'm hoping that it's going to work.
The pain of the heat of that fever.
The flu flattened me.
I was really worried that I was going to give it to my kids.
4 weeks on the couch.
Couldn't go to work, I couldn't do nothing.
I couldn't eat or drink. I had an immunity issue, so I can't be near the flu.
The flu triggered my asthma.
Very sick.
Just good.
You really worry about your baby?
It can be very deadly.
Then a big trip to the hospital.
And I just remember thinking, this is the flu.
You never forget the flu, so don't forget your flu shot. Authorised by Victorian Government, Melbourne.
Okay, so I think those are quite useful little sound bites to show us exactly what Mike was saying about the fact that the flu isn't just a normal cold. It can really make you feel pretty unwell and, sadly, on occasion, be very serious. So flu is a virus, and it is really highly contagious. So it can spread very easily. So it spreads through droplets. So when you sneeze or when you cough, it can spread at least 2 meters. And there's a wonderful video on YouTube which actually shows someone sneezing on a London bus. And that sneeze goes right to the end of the bus. So it spreads very easily. And then those droplets will hang around in the air. So if you're in the same airspace, you may just breathe it in. The other thing that happens is that those droplets then sort of settle, and they'll settle onto all surfaces. So if you then touch those surfaces, you can then end up, and you put that, your hand that's got the flu virus on it to your nose or to your mouth, you can infect yourself that way as well. So it's really important that actually trying to cover our noses and our mouths when we're sneezing and washing our hands all the time is really vital in terms of protecting ourselves from the flu. So there's 2 types of flu virus, particularly that we're aware of, and that happen most seasons. So there's influenza A, which is the one that we mostly hear about, and that tends to cause slightly more severe disease than influenza B. And often what happens is that you get in the start of the season influenza A cases, and then a little bit later in the season you'll get the influenza B cases. Everybody can be infected by the flu. No, it doesn't discriminate. But what it can tend to do is cause a varying degree of illness. So people get different experiences. So if you're fit and healthy, you may well feel pretty awful for about 7 days and then recover. If you have some sort of vulnerability that makes you more likely to have severe disease, so that might be that you're older, and that your immune system doesn't work so well. It might be that you're very young, or it might be that you already have problems with your lungs or your heart, for example, that mean that that additional problem of having the flu virus on board and having to fight that puts your body under a lot of strain and can cause really serious illness and, as I say, occasionally fatalities. So one of our best mechanisms for protecting ourselves is the flu vaccine. And what we do is we focus on providing flu vaccine to all of those who are most at risk of serious disease. So that would be people over the age of 65, children aged 6 months to 5 years, pregnant women, people from Aboriginal and Torres Strait Islander origins, or if you have chronic conditions or a weakened immune system. However, even though we provide those for free, and those groups are the ones that we were most concerned about for most severe disease, it doesn't mean that people not in those risk groups are somehow immune from flu. And as I say, flu doesn't discriminate. Anyone can get it. So this is a graph of what's happening through the flu season. I'm hoping my pointer works. Yes, absolutely brilliant. Okay, so along the bottom we have months of the year from 2017 through to 2018 through to 2019. And up this side we have the number of notified cases of flu. And in the pale blue or green we have influenza A, and the black is influenza B. So you'll probably all remember the 2017 flu season. I wasn't in Australia at the time, but I do remember hearing about it. There was a really big peak of cases through July, August, September and October. And I believe that over that year there was something like 42,000 cases in total. Last year was a really mild year. And then it seems that around August and September we started getting more cases. Now, that is the sort of time of year that if you lived in England would seem normal to be having flu, but if you live in the southern hemisphere, that's really unusual. So we've had something unusual going on where we've had cases all the way through the southern hemisphere summer. So while you may be hearing in the media quite a lot about there's a 5-fold increase in cases, this is a crisis, I think it's really worth bearing in mind that actually we're not seeing these levels at the moment. The reason we're seeing so many extra is because the flu for some reason started early this year, and there's various hypotheses about why that might be. The other thing that and what it doesn't mean is, what I can't tell you now is what's going to happen. So it could be that this has just been an early season and it's all going to tail off. It could be that it's just going to grumble along at this level, and it could be that there's another strain or another problem that suddenly means that it takes off. And it's really impossible to predict that. So we just have to watch and wait and continue all of the surveillance we're doing and the counting of cases to see what's going to happen. The other thing that you'll be aware of course, is the reports of deaths in the media. I need to be clear that we're not notified of every single death. We're only notified of deaths that occur in aged care facilities because we're notified of those outbreaks there. So the numbers that are being reported, which is 23 deaths in aged care and 3 deaths in children, is definitely an underestimate of the number of deaths that are actually occurring from flu. So this is our role in Department of Health and Human Services. So this is a standard diagram of how the department is organised. The key bits, oops, sorry, that wasn't helpful. The key bits are regulation, health protection and emergency management is where I sit in the department. And we are doing disease and outbreak response. We're notified of every laboratory confirmed case of influenza. And so we're monitoring what's happening within the department, but also with a whole load of other partners that I'll be talking about in a minute. My part of the department also does all of the immunisation procurement and distribution. We work with all the providers who are providing the flu vaccine to make sure that eligible groups are getting it, that people understand which is the best vaccine, etc. And we have a small number of public health doctors like myself who support all of this. We work very closely with our communications and media team, which is elsewhere in the department, that is helping us communicate the key messages that we need to help protect people from the flu. And of course, we're working with our hospitals and our aged care and rural regional health colleagues because they're often the bit that bears the brunt. So this is a really horrible picture, I'm aware, but it's just really to show you quite how complicated flu surveillance is. So all of these different elements here are looking at various different aspects of the flu season so that we can understand how severe it is, how transmissible the infection is, pick up any issues. So in particular, we have a surveillance that's looking at those severe complications, and we have a surveillance here that's working with general practitioners, so seeing people who are coming to the general practitioner for advice. So let's say you get influenza. I'm sure several of you in the audience have had flu yourselves, so this may well be very familiar. But there's a usual fairly standard course that lasts about 8 days. It can last up to 2 weeks in terms of recovery. But you start off by feeling, you get a very high fever, so over 38 degrees, headaches and muscle pains. You'll have a cough and sore throat, sometimes a stuffy nose. After a few days, that fever and muscle pain decreases, but you may get more chest discomfort. Sorry, I'm knocking my microphone there. And you may feel pretty tired and flat. And then by about day 8, the cough and tiredness may continue, but otherwise, generally, symptoms will decrease. And as I say, occasionally it can be very, very severe and cause complications, lead on to pneumonias and things like that. And even though we recognise that flu can be most severe in people who already have some vulnerabilities, it's worth remembering that flu can actually affect very healthy people seriously too. And that's why it's so important that everybody gets their flu shot. So, when to see your GP? We know very well that most people who have flu won't go and see their doctor. They'll manage it perfectly well at home. But there's always questions about, well, when is the time to call a doctor? So if you're in a risk group and you start getting flu-like symptoms, that would be a good idea. Or if you are finding that you're getting very severe symptoms. So the sorts of things that we would be very worried about is if you're really having difficulty breathing, if you're getting pains in your chest, if you're starting to feel dizzy or confused, if you're vomiting, or if you're actually developing a rash. If you go to see your GP or a hospital doctor, what they'll do essentially is ask you stuff about how you've been feeling, how long your illness has been going on, who you've been, if you've been in contact with other people with the flu, for example. They'll perform a physical examination, so they'll listen to your heart and your lungs and take your temperature, take your blood pressure. They'll decide if they need to take a swab for the flu, and they don't always do that, because from an individual perspective, whether it's the flu virus or whether it's one of these other respiratory viruses, it doesn't make that much difference, because the management, the treatment of you is exactly the same. It's about rest, it's about staying away from other people to limit the infection, it's about taking painkillers like Panadol, and drinking plenty of fluids. Occasionally, a doctor will consider an antiviral medication to try to reduce the length of the illness and potentially to reduce further transmission. These antivirals need to be given within 48 hours of the onset of the infection to be actually useful. And they will consider various things like how likely is the flu, do you have any other illnesses ongoing like chest or heart problems, and if you have any contraindications, so allergies, for example, to something in the antiviral, which would mean that it wouldn't be a good idea to give it to you. So as I've mentioned on several occasions, a flu shot is really your best protection against getting the flu. It's the most important measure that we have, both to prevent flu, but also to prevent severe disease. And we recommend an annual influenza vaccination for all people aged over 6 months. It needs to be annual because the flu virus is very smart and is constantly changing. And one vaccination, unlike some things that you can be vaccinated once and that protects you for life, the flu vaccine is such a formidable enemy. Not the flu vaccine, sorry, the flu virus is such a formidable enemy that we need to keep changing the formulation of the vaccine to keep up with it. And as I've said, there are some people for which flu vaccine is free. And so far this year, we've distributed over 1.5 million doses of influenza vaccine to GPs, community pharmacies, and local councils across the state. So, various ways to protect yourself and your loved ones. As I've said, when you cough and sneeze, you spread droplets. Many people cough into their hands, but the trouble then is if you put your hand down, you continue to spread the infection. So we advise people to try to cough into their elbow. Regardless, not everybody is going to do that, and you can't kind of catch all of those droplets anyway that way, so it's really important to keep washing your hands. That'll protect you from flu, but it'll protect you from a lot of the other infections that go around, particularly at this time of year. If you're sick, it's important to stay at home. Don't kind of try to persevere and go into work or school, because you're just going to continue to spread the infection. So it's not good for you and it's not good for the people around you. So we'd really, really recommend staying away from school or work, and particularly trying to stay away from people who you know may be more at risk, both of the infection or severe complications. And lastly, don't forget your flu shot. Thank you.
Great. Thank you very much. Now, I forgot to mention the format that we'll use this evening. What we'll do is take questions about all the talks at the end, so I think that'll give us an opportunity to absorb everyone's talk and have the group here as a panel. So, it's a great pleasure to introduce Professor Kanta Subbarao, who became Director of the World Health Organization Collaborating Centre for Reference and Research on Influenza here at the Doherty in 2016. Prior to that was Chief of the Emerging Respiratory Diseases section at the Laboratory for Infectious Diseases National Institute of Health in the USA. Her work focuses on emerging respiratory viruses of global importance, so pandemic influenza notably, but also the SARS and MERS coronaviruses, the immune responses to their infections and vaccination, and I forget the next bit, Kanta, I'm terribly sorry. But anyway, Kanta's got a really terrific talk for you this evening, and I won't spend any more time introducing her, but I'll just pass the floor over to her. So,
great,
Kanta.
thank you.
So I'm going to talk to you about the illness and the virus and the vaccine. So you'll hear some reiteration of what Dr. Bone just told you, but it doesn't hurt to hear it more than once. So you will see some of these messages repeated. So the World Health Organization put together a beautiful calendar this year with information, with sketches drawn by children, and they've attributed these drawings to the children with their ages. And so this I thought was very pertinent, where we're talking about the symptoms of influenza infection that you just heard about. And here's an 11-year-old from Switzerland who's drawing of what happens with flu. So as you've heard, an uncomplicated influenza infection is a sudden onset illness with systemic signs including fever, headache, and body ache, as well as respiratory signs. So the big issue is with complications that follow influenza that can range from pneumonia, bronchitis, sinus and ear infections, and a worsening of pre-existing health conditions such as underlying lung or heart disease. So one of the questions that we're often asked is, how do you distinguish between a cold and influenza? And so briefly, and this is a slide that was put together by the Centers for Disease Control, some of these things we've already talked about. Influenza has a very abrupt onset. A common cold has a more gradual onset. Fever is more common with influenza, more rare with colds. Aches and pains. I mean, people tell you that everything hurts with influenza. And that's a really big part of the illness with influenza, and less so with the common cold. Sneezing is common with both. Stuffy nose, sore throat might be more common with the common cold. Chest discomfort and headaches are more common with flu. So there are ways to distinguish them. And in addition to the sudden onset and the constellation of systemic symptoms associated with influenza, the recovery period is longer with influenza than with the common cold. So as you heard before, it's people at the extremes of age that we see most often hospitalized or becoming ill with influenza. And they include children. So these are, in purple, are the notifications of influenza, and in magenta, I guess in pink, are the hospitalizations. And you could see that there's a peak in the young children and in people over 65 years of age. And when you break this 0 to 4-year-old down, it's really in the children under 6 months of age, under 2 years of age. So we have more infections and more hospitalizations at the extremes of age. So Dr. Bone covered this a little bit, and I will highlight, because I trained as a pediatrician, I'll highlight what to watch for in children, because she's already told you what to watch for in adults. So what are the warning signs of a severe influenza illness? In children, it would be fast breathing or trouble breathing. They can get a bluish color. They may not be drinking enough fluids. They may not wake up or interact. It may be very irritable when being held. And what we watch for also is sometimes in all ages, you can have flu-like symptoms that get better and then get worse. So what that worsening is often a secondary bacterial infection or a complication. In infants can present with fever alone, with no respiratory signs. And so it becomes very difficult to diagnose influenza in a very young infant because they may present with very generic, very non-focused findings. So they may just stop eating, be very irritable, be dehydrated, so they're not crying tears, and they don't have as many wet diapers as usual. So these are the things to watch for in these different age groups. So the burden of influenza in Australia is on each year, on average, not counting the really big year of 2017, but I guess that was evened out by the mild year of 2018. On average, we see about 3,500 deaths, up to 18,000 hospitalizations, and 300,000 GP consultations. So you've heard already in 2019, we've had more influenza activity than usual in December and January, which should have been a really quiet period. And then there was an increase in March and April. So when we first started seeing this, we weren't sure whether it was a continuation of the summer or interseasonal activity, or whether it was an early onset of the flu season. And as you've heard, we've heard of outbreaks in aged care facilities in several jurisdictions. So the illness that we're referring to is called influenza, and the viruses that cause this illness are also called influenza. So the viruses are called influenza viruses. They come in many different types. They come in 4 types, of which 2 cause epidemics of influenza. As you've heard, they're influenza A and influenza B. Currently, we have 2 strains of influenza A and 2 strains of influenza B that co-circulate. What's important to know is that the clinical illness caused by any one of these 4 are indistinguishable from one another. And so that is why, in order to determine which of these strains is causing influenza, you really need a diagnostic test to distinguish. But the clinical illness is essentially the same. So this is a schematic of the virus, and this is another schematic of a virus drawn by Lily, an 11-year-old from China. So vaccines, as you heard, are the most effective control measure that we have available. So you heard already about how the virus is spread through a cough, and you heard about the virus particles laden with virus that can settle out or can remain suspended. And here's an action figure showing you exactly how the virus is spread into the environment. And you can acquire the virus through direct contact on a contaminated surface, so think in public transport, handles, seat arms, and so on, and then also airborne particles that you breathe. So as we both said, the vaccine is essentially our best protective measure, but the virus continuously evolves in nature. So you've heard before, and we certainly know of vaccines that if you get once in your lifetime, you're doing well and really may need a booster depending on age. But generally speaking, those pathogens tend to be very similar, and so one vaccine can protect you against the whole range of disease. But influenza is different, and it's the only vaccine that has to be updated annually. And it's updated annually because it changes in nature. So right after World War II, the World Health Organization recognized that influenza was a global disease. And so they developed a network to monitor influenza activity. And it is the oldest network and one of the most successful networks at the WHO. And so what they did was they asked each country to name at least one national influenza center. And that's what's abbreviated as NIC. So we have 3 in Australia, 1 in Sydney, 1 in Melbourne, and 1 in Perth. And each of those are shown as these blue triangles. In addition, there are 5 collaborating centers around the world to which these national influenza centers provide information. And the 5 WHO collaborating centers are in London, in Atlanta at the Centers for Disease Control, in Beijing, Tokyo, and Melbourne. So these 5 centers communicate with each other and monitor activity and characterize viruses. Our main goal is to recommend what should be updated in each year's influenza vaccine. And that is based on studying the viruses that are sent in by the national influenza centers to see whether they have changed or whether they continue to be well represented by the component that's in the vaccine. So the vaccine contains, the standard vaccine contains 4 components, 1 representative strain for each of the 4 strains that can cause influenza. So 2 A's and 2 B's. There are enhanced vaccines that are available for people over 65 years of age that either are high dose or have an adjuvant in them, and those are trivalent vaccines with 2 influenza A strains and 1 influenza B strain. So this shows you this is the size of the binders that we look over. We spend a week looking over these data, poring over this information. Each center looks at thousands of viruses a year, and we look at the data from around the world. And this is a recent photograph of the people who participated in deciding the vaccine strains for the Northern Hemisphere in February. So the committee meets twice a year to recommend what suitable strains to be included in the vaccine. There's a decision made in February for the Northern Hemisphere winter, and a decision made in September for the Southern Hemisphere. So the vaccine that people are getting now was based on a decision made 6 months ago. And the reason for that is that it takes that long to manufacture, distribute, and deliver the vaccine. So we recommend a vaccine strain change if the circulating viruses are anticipated to be different from what's in the vaccine. And the recommendation to the WHO is just that, it's a recommendation. And the national authorities then look at that recommendation and decide whether to accept it. So this is just a picture to show you how often the strains change. And you can see from this that the influenza A H3 virus changes much more in nature, and so we're playing catch up much more and changing the vaccine strain more often with H3 than with H1 or influenza B. So I'm just going to close with a few words of some of the myths and facts about influenza vaccines. You've heard most of these, and I'm sharing them with you so that you can go out armed with this information and you can refute these comments when they're made. So one of the common ones is that influenza vaccines can cause influenza. So the vaccines that are licensed in Australia do not contain live virus, so they cannot cause influenza. That's it. Influenza vaccine is not effective. The vaccine is actually highly effective against H1N1 and influenza B viruses. Admittedly, the effectiveness against the influenza H3 strains is not optimal and has not been for the last few years, but it's an active area of research. Healthy people don't need to get vaccinated. Anyone can get influenza, and being fit and healthy doesn't protect against infection, so if you want to prevent influenza, vaccine is a good way to go. People shouldn't get vaccinated with influenza if they're sick. So minor illnesses without fever are not contraindications to vaccination, especially if the person's at risk for serious complications. And then there's a really common one, I was vaccinated and got sick anyway, I'm never going to do this again. Now there's several possibilities. Everything gets called flu. So the infection could have been caused by another respiratory virus, a rhinovirus, an RSV, anything. People may have been exposed to influenza before they got vaccinated and made antibodies. The vaccine could be a poor match with what is circulating. And it's important to remember that the goal of vaccination is to prevent severe illness and death. It does not completely prevent all influenza. So if it ameliorates or moderates the course of illness, that's not bad. So with that, I will close and thank my colleagues. We are funded by the Australian Government Department of Health. Thank you.
Thanks very much, Kanta. Particularly like that myths slide. That's terrific at the end there. So a complete change of perspective now. I'd like to invite Kiara Perrin, who was infected with influenza last year and never forgot it, to come and join us and talk to us about her experiences of getting ill with flu at work and recommended to go to hospital but needing an ambulance on the way, as I understand it. So love to hear the story, Kiara.
Thank you. I guess I'll start with saying thank you for having me. As I've been introduced, I'm kind of just a case study. So I'm 22 years old, fit, healthy. I'm kind of one of those unusual, cases. So I got the flu in December last year, which is summer, so very odd time to get the flu. But basically, I guess my symptoms, I got home from work one day, I was quite tired, went to bed quite early, got up the next day, went to work like everything was normal. But I remember thinking that morning, my arms are a bit heavy. I wonder if it's the flu, that's a bit odd. In general, I'm kind of okay, apart from the fact I went to bed early that night. But yeah, I got to work and it was a bit bizarre. I lost my voice, so I started just creakily losing my voice, but it got to the point that I couldn't talk at all. I had no voice at all, so it made work quite difficult that day. And yeah, then I started getting breathing issues. So sitting at my desk, struggling to breathe. I was like, okay, this is a bit odd. Took my temperature, had a temperature, went to the doctors after work. Basically straight after work, went straight to the doctors. By the time I got there, I was definitely not well. And the doctor said, look, you might need a chest x-ray. I'm not really sure what's going on. It's a bit late. Why don't you go to the hospital? And I was declining very quickly. So I called my parents and they came and picked me up from the doctors because I was definitely not fit to drive. And on the way to the hospital, basically my breathing got to the point that I felt like I couldn't breathe at all. And my oxygen levels got quite low, and we happened, very luckily, to drive past an ambulance on the way to the hospital because there was a bit of traffic, it was peak hour, so we were very lucky. Got into an ambulance, they basically were like, yep, get in, you're going to the hospital. Put all the wires and everything on me, my oxygen was low, went straight in, got in, they did a bunch of tests. The big issue with me was that I had a bit of a stridor, so basically, not medical terminology or anything here, but my breathing pipe was covered by like a little flap in your throat. So when I breathed in, it was covering it. So that was my main issue at the time. And we're like, it's really bizarre for that to happen. And they got this camera and they put it down my nose and had a look at my throat and like, oh, your tracheitis is, your trachea is quite swollen. It's not, definitely not, nothing's working properly or anything like that. Did a test, came back that yes, I do have the flu. At that point, I was still declining, not breathing properly at all. They put me on steroids, I believe, and I was put into the ICU. Then I was in there for about a week in the ICU, so again, fit, healthy, no previous issues. In the ICU for a week, and then when I started breathing a bit better, I had a bit of a stridor, or a really bad stridor. Couldn't talk at all, still wasn't eating. I lived off sausagen, I think it was, for about a week. And then got put into the normal part of the hospital for a few days. So I think I spent just over a week in hospital. And when I was in the ICU, they had this mask that I had to put on my face, which literally pushed air down my throat. So I was on that for a week. And then still on the oxygen when I went into the normal ward. Came home, and I was off work for a while, but obviously it's the flu. I was coughing and things like that, and it bruised all my ribs. I actually thought I broke my ribs from it as well. So I had a lot of issues with that. And yeah, came home. I think I was sick. It ended up being around three to 4 weeks that I was significantly impacted by it. And being quite young, I was getting paid casually. I wasn't on a salary or anything like that. So that was a massive factor that influenced me. So yeah, I think, looking back at it, taking a few minutes out of your day to go and get the flu vaccination, it's not really that big a deal compared to missing out on a month's pay almost of work, and get to the point where there's bills and things to pay, and it's really, when you put it into perspective, it's not much that you shouldn't be paying attention to. So yeah, that's my story. Definitely going forward, I've definitely had my flu vaccination this year, to say the least. And I would honestly say to anyone that's, thinking about getting the flu, you definitely do not forget the flu. I know I definitely won't. And it's, in the scheme of things, it's a little thing to go through. I personally absolutely hate needles as well, so that wasn't anything I was looking forward to doing, but definitely get it done so you don't get the flu. Yeah, that's my story.
Well, thanks for sharing that. That's quite a story, isn't it? So, yeah, that's. I think that's the worst story of flu that I've ever heard firsthand from someone that suffered it. So, thanks for sharing with all of us tonight. Which brings us to our last speaker, which is Professor Lorena Brown, who's one of Australia's leading influenza virologists. She leads a group here at the Doherty that research on control and understanding of the influenza virus. She's part of a large NHMRC funded program that's interested in why some individuals and some communities get worse outcomes from influenza than others. So the work of the group's contributed to some major advances on the way to improve medicines and vaccines for flu, and also made some major discoveries about how the virus swaps its genes and how that might contribute to human disease during a pandemic. So, Laurie.
Thank you, Mike. Well, good evening, everyone. As lucky last, I'm here to tell you to look forward and to think about how we treat flu into the future. And I must just preface this by saying there's a lot of fantastic research on influenza being carried out here at the Doherty, much more than I can talk about in 10 minutes. So I've just really picked 3 areas that I'd like to talk to you about, not because these are necessarily the best, but they cover a wide range of different areas, and I'm pretty familiar with each of those. So let's talk about these. So I've picked to talk to you today about 3 different things. A new compound that enhances and expands our immunity to the current influenza vaccine, and that's research being carried out by the Jackson Laboratory, some members of which are here, I can see. Also, the second thing, identification of shared T-cell targets on the virus that do not vary, and I'll explain what that means and the implications of that. And that's work done by Catherine Kadziecka's laboratory. And lastly, some work from my own laboratory about antiviral drugs that prevent influenza for up to a month after only a single dose. So in order to understand these different areas, we first have to understand something about the virus and how it replicates. So viruses are so small we can't see them by a normal light microscope, but we can see them by bombarding them with electrons. And here's a picture of the flu virus under an electron microscope. And as you can see, the virus on its surface has these different protein spikes, and they're the parts of the virus that bind to the cell, because viruses have to grow inside cells. They can't replicate outside a cell. And there are actually 2 different proteins on the virus surface. Here's just a model which corresponds to the virus itself. The main protein on the surface is represented here in blue. There's more of it than the other one, represented in red. And this blue one is the hemagglutinin, or HA. And that helps the virus to get inside a cell to start replicating. The other one is the neuraminidase. It's a mushroom-shaped protein, and here we are looking down on the top. You can just sort of see what it really looks like here from the side. And that helps the virus to get out of the cell that it is infected. And it's these 2 proteins that Cantor was talking to you about that change over time. And so this is why we have to keep altering our vaccine. So what's being infected when you get the flu are the epithelial cells that line our respiratory tract. So here we are. This is just a model of a respiratory epithelial cell. The virus will bind to that cell via its hemagglutinin, which the hemagglutinin will engage with a receptor on the cell and get inside. What happens then is that the virus is broken down into its components, and each of these components are replicated over and over again, so that thousands of different copies are made, and they're all assembled into new virus particles. And then once these virus particles are assembled, they are released from the cell and go on to infect other respiratory cells in the respiratory tract. And it's the neuraminidase that helps those viruses get out efficiently and replicate in more cells. So if you think about it and if you visualise it, one virus goes into a cell, but over 10,000 viruses come out. So this is a picture that one of my students took of an epithelial cell that's been infected with one virus particle, and each of these little spheres that you see on the surface are viruses coming out of that cell. So that's what's happening in our body, and that's what our immune system has to fight. So when we get infected with a flu virus, we make these protein molecules called antibodies, and they target the hemagglutinin and the neuraminidase. They will bind to those proteins, and antibodies to the hemagglutinin will block the virus from getting in. So they're really a fantastic defence mechanism that we have. And antibodies to the neuraminidase will stop the virus efficiently getting out and being released and going to infect other cells. And the nice thing is that these antibodies are not just made in response to infection, but they're also made in response to the vaccines that we have currently available to us. Now I need to introduce you to a different type of immunity. This is the cytotoxic T cells. So when we're infected with influenza virus, our bodies also make these cells which are called cytotoxic T cells or CTLs. And they don't recognise the virus particle like antibodies do, but they recognise cells that have been infected with the virus. And they do that by recognising small parts of viral proteins that are presented on the surface of the infected cell. These are just little peptides, about 7 to 10 amino acids long, and the cell puts them on the surface to tell the immune response that I'm infected, kill me. So it's a strange thing, but it doesn't matter. We can make more, we can grow more epithelial cells. So the aim of this type of immunity is to kill the cell before those 10,000 viruses are assembled and released. And it does it by, this cytotoxic T cell does it by the release of these cytotoxic granules into the cell which kill the cell. Now I've got a little movie for you to show you. So the big cell here is a flu-infected epithelial cell, and the little guy is a cytotoxic T cell. And here it is interacting with that cell, and this cell has lysed and will crumple up and die. So you can intuitively realise that these sorts of cells do not prevent infection, but what they do is they lessen the severity of infection because they're reducing the viral burden in your body by killing cells before they can secrete more virus. Now, these cells are not made in response to our current inactivated vaccines that we have in Australia. So it's a different arm of defence that we're not utilising by our vaccines. Right, so let's go to the first one, a new compound that enhances and expands our immunity to influenza vaccines. So this molecule has been worked on by the Jackson Group for a lot of years now, and they've finally got it to a stage where it's working really well. This molecule is called PAM2-CIS, and it mimics a part of a pathogen that our immune system has evolved to recognise. So as soon as PAM2-CIS enters the body knows that it's foreign, it's a danger signal. So if you mix this molecule, which by itself is very harmless, if you mix it with our current vaccines, it really enhances the levels of antibody that can be made. And we can get the same response with much lower doses of vaccine antigen. And that's really important when we're particularly in a pandemic. So when a pandemic comes, we need to make vaccine really quickly, and everybody needs the vaccine, because the virus that comes in a pandemic is very different to what we've had before. So no one has good enough immunity. We need to have vaccines on the scene very quickly, and at the moment they're usually made too late to really tackle the peak of the response. So just in some animal models that we use to test our vaccines, you can see here that each little circle is an individual animal. If they have no vaccine, if we take them and look at how much virus is in their lungs, we can see 10 to the 6, so 1 million viral particles if you don't do anything else. And here, if we give them vaccine, but at such a low dose that it won't do anything, we see that nothing has reduced that level. If we mix that same amount of vaccine with PAM2-Cis, all of a sudden we now see a greater than 99% reduction in the viral load in the lung. And so clearly that's very, very beneficial. And Kanta has already mentioned to you that for the elderly now, we're starting to give vaccines that have an adjuvant. And this is an example of an adjuvant, but a better adjuvant than what's out there, I think. So the other thing about PAM2-Cis, we know that this response, this reduction, if you use the same vaccine and match it to the virus that you challenge those animals with, we know that that reduction, that 99% reduction, is due to antibody. But the nice thing about PAM2-Cis is that if you can bind it to the components of the vaccine, it will induce this other arm of immunity, these CTLs. And the Jackson lab have found out a way to do this, to link it to the vaccine components by virtue of charge. So when physically linked in this way, the vaccine can induce these cytotoxic T cells that I was telling you about. And the benefit there is that cytotoxic T cells are much more broadly cross-reactive than antibody. So they will give you protection against not just the strain that matches your vaccine, but strains that are slightly different. And so this means that the problems we have with mismatch is not such an issue. So if we can't predict what's coming with 100% accuracy, it doesn't really matter, because we'll get some protection from these cytotoxic T cells. And here we see with a non-matched viral challenge that we're still getting 95% reduction. This component, this PAM2-Cis, is good in another way, because it induces yet another form of immunity that we call innate immunity. And that's an immunity that works immediately, whereas our vaccines, our normal vaccines, take several weeks before they induce antibody. But this innate immunity works very, very rapidly. Okay. Our second research highlight is from Catherine Kadziecka's lab, and it's about identifying those little peptides that are recognised by cytotoxic T cells. But she has discovered that these peptides can be present in a whole range of different viruses. Now, Kanta explained to you that we have type A influenza and type B influenza. They're the main ones that give us the severe influenza that we typically vaccinate against. There's also influenza C, which causes mild infections in children, and we tend not to vaccinate against that. So mainly our efforts are in the area of A and B. But in Catherine's lab, what they do is they try and identify those peptides that are targets for cytotoxic T cells, and recently they've found some that are present in all A strains, influenza A strains, in many, many influenza B strains that they've tested, and also in influenza C strains. And so they know that these peptides will induce broadly cross-reactive cytotoxic T cells, and these epitopes are really highly conserved. And they can find those T cells, if they use the peptides to pull out the T cells from people, they can find them in healthy people. So we know that they will induce these cross-protective T cells in people. So in our animal models, they can vaccinate with these peptides, and they're protective against severe disease, which is what we'd expect. So they're functional. And if you think about it, if you can put these epitopes that don't change into our vaccine or into a new type of vaccine, then it means that we don't have to vaccinate every year, because these epitopes are highly conserved and they will be enduring in those viruses. So our immune response will be lasting, because that part of the virus does not change. And lastly, for some work from my own laboratory, and we're taking a different tack now. We're going to talk about antiviral drugs. So our first speaker, Dr. Bone, talked about the use of antivirals, and typically what we use antivirals for is to treat a patient who's already infected. So a vaccine may not have worked, or they may not have been vaccinated. They have severe flu and it needs to be treated. So we have antivirals like Relenza and Tamiflu, but as we heard, they only work if you start giving them 2 days after you're infected. And you have to give them twice a day to keep those levels up. And so if you think about it, Australia does have those antivirals stockpiled, and we plan to use them for our first line of defence workers in a pandemic. But to use them twice a day, every day, there's no way a stockpile would last for long enough to do any good. So our current antivirals are no good at preventing infection. So what we're working on in my laboratory, in collaboration with a small Australian biotech company called AusBio, is a new type of antiviral drug. And we're aiming for something that works if you give it once, one shot once, not twice every day, one shot once. And we've come up with something that we think is really quite remarkable. So the basis of this is that we know the hemagglutinin, the HA molecule on the surface, this blue one, normally looks like that. But when you treat it with acid, which normally happens inside the cell, for normal processes that the virus might have to go through to replicate. If you treat the virus before it gets into a cell with acid, the hemagglutinin will open up like this. And the hemagglutinin in this form cannot bind to a cell, so it cannot get in and infect that cell. So what we do is we have these compounds that have 2 parts to them. The first anchors the compound to the virus, excuse me, by binding to the neuraminidase. The second part is a long chain of acidic residues that create this environment that opens the hemagglutinin out like this. And that way it cannot bind to a cell. So here we've just taken epithelial cells in culture and compared and infected them and compared different doses of our different antiviral compounds. There's two here, we just call it MD185 and MD345 are two experimental compounds. And we're comparing it with zanamivir, which is the current antiviral that people use now. And we find it's 1,000-fold more potent. So you can get the same effect with 1,000-fold less amount of antiviral drugs than what we would use with Relenza. We also find that it has this amazing capacity to last within the respiratory tract. So we give this drug to the respiratory tract and it sits there. So after one dose, we can still see protection in our animal models against lethal infection for 40 to 60 days, which is quite remarkable. And we can also make note of the fact that we only need one dose compared to the current antivirals. And finally, we can also use this to treat established infection, and we can go out a little bit longer than the 2 days that we need to start treating with the current antivirals. So I hope I haven't confused everybody. I hope I've shed some light for how we might treat these infections into the future. We've got a lot of tools at our disposal, and maybe even a combination of some of these things might put us in good stead. So even though a one-shot vaccine is not around the corner now, because these things take time to develop, I think the future is a lot brighter. So thank you, everybody. And I'll just finish by putting up a list of the people who gave me their slides and who have been working in these different groups on these antivirals. Thank you.
Great, thanks Laurie. So could I invite all the speakers to come to the front and form a panel? We have Finn and we have Rebecca with mics, and we'll take questions from the floor for all of or some of the panel. So we have a couple of hands, and second up the back.
Is this working? Yeah. Just going back to the very beginning, the slides in the movie you showed about people with the flu, the symptoms they complained of. Somebody said they were there for 4 weeks. Now, he didn't have flu, he had Q-fever. So you got the diagnosis wrong then. Flu doesn't go for 4 weeks.
Well, I think we have to remember that these are people reporting their own experiences, and so the recovery might have taken them 4 weeks. You know, it's very difficult to tell from that information what the likely cause was. But yeah,
He must have been a school teacher, was he?
Sorry,
a school teacher?
I really have no idea.
Okay, thanks for that. Up the back.
Yeah, my thought was rather than sneezing into your elbow or your hand, bring back the handkerchief.
Yeah, now that's an interesting one. The trouble with handkerchiefs is that people tend to put them in their pocket and then kind of get them out repeatedly, and you can actually end up spreading more infection that way. So one of the other pieces of advice is to ditch the handkerchief, but use tissues. Use them once and throw them away immediately, and then wash your hands.
Yeah, the last time I had a cold, I'd used tissues, and I found that the nose was getting a lot sorer with tissues. I went back to handkerchiefs, and they were a lot softer on a delicate nose.
Yeah, and I've had a similar experience myself, so I do know that, tissues can sometimes make things very sore. The alternative is to have a whole stack of hankies and to use them once and put them straight in the wash.
But also, because I hear your pain, there are the tissues with aloe vera in them, and they are a lot gentler on the nose. So if I could make a recommendation, it would be that.
How well does the current vaccine match the circulating strains?
Could you say it?
Did everyone hear the question?
How well does the current vaccine match the circulating strains at the moment?
So we currently have, so if you're talking about right now, we have more H1N1 than H3N2, although both the influenza A strains are circulating. We have very little influenza B activity. It's too early to tell how well the vaccine strains match. We're reasonably confident that the H1N1 will match well. The H3N2, there's a lot of genetic heterogeneity amongst the viruses that are circulating. So the earliest and people's response to the vaccine depends on a number of factors, including the match between the strains. It's also influenced by the age of the person, their general health status, and their prior experience with influenza. And so we typically get a feel for how well the vaccine has performed only about halfway through the season. And that's when we would get an interim vaccine effectiveness measure. So the vaccines, the H1 and B appear to be well matched. H3, there's so much heterogeneity that we basically have to see which of those strains dominate.
How long do you expect the vaccine to last? Like how many months?
So that's a good question. The antibodies take about 2 weeks to develop. So protection from vaccine takes about 2 weeks from the time of vaccination. We generally find that the highest levels of antibodies, which essentially are the mediators of protection, happen about a month after vaccination. And then they stay fairly high. In fact, we've just finished a study where we found very high levels of antibody out to 6 months post-vaccination. We anticipate that by the end of the season, by the time you're due for your next annual vaccination, those antibody titers do decline.
May I direct my question to the young lass who sadly suffered a very severe circumstance, and then throw that out to the panel as well. How long before you felt fully recovered from this terrible experience? And then to the panel, when you have a severe case, such as described there, is that about the average time it takes to recover?
I think mine particularly, I was in hospital for over a week, and then I would probably say it was around a month in hospital for a week, and then I was in bed for another 2 weeks after that. But my whole body was definitely really affected from it because I was straining to breathe so much. So my ribs, that pain went on for months, like at least 3 months after. I still felt pain, but I would probably say it would have been around the month mark until I felt better.
What I was after is at least 3 months before you it was at least 3 months before you started feeling you coming back to normal, wasn't it?
Or no, it was a month until I felt like I had enough energy and things to be able to do things day to day. In terms of like before I got the flu, I was going to the gym every day and just general living things. I couldn't do that at all for a while because of how badly I hurt my rib cage and whatnot. And even still, I found that when I've gotten sick since, like even if I had little colds or anything like that since, I get a bit of a stridor back as well. So it's definitely something I have to watch. I don't know if it's a long-term issue or something that I've developed from the flu or whatnot, but a month until I was feeling better, but then the ribs and everything was about 3 months, yeah.
And then just back to the panel, in severe cases like that, is that 3+ months a normal period of inconvenience?
Shall I start? That doesn't sound too surprising to me, to be honest. When you've been so unwell that you've ended up in intensive care, you've been on one of these masks forcing oxygen into your body, it's little wonder that you had all of this terrible pain around your rib cage, etc., going on. And that whole experience of being in intensive care and your body fighting the virus will take a significant amount of time to recover, and you're not eating necessarily properly and all of those things too. So I'm not surprised by that. And you were healthy and well before you got sick as well. So if you were unhealthy before you got sick, you clearly got further to get to recover.
If you have the vaccine now, or I've already had it, and then you travel overseas, at the end of 6 months, what immunity do you have for an overseas flu that could be different to the one we...
So that's a good question. As I said, the antibody levels we found last, at reasonably good titers to about 6 months. So the real issue is somewhere between 6 and 12 months when they might decay, and that might happen to be when flu is circulating in some other part of the world and you're traveling to that part of the world. So in terms of the strains, they are often not completely different from each other. We update the vaccine to try to get an optimal match. But if you were vaccinated and happened to travel within a few months to an area where there's an influenza epidemic, you should be okay. There are parts of the world in the sort of around the center of the globe where influenza is present year-round. So you could end up visiting the tropical country where there's influenza at a time when your vaccine-induced immunity might be lower. So recently, the shelf life of the vaccines have been extended to 11 months of a year, so that if you're traveling overseas and it's been a long enough time since you got the previous vaccine, you could get revaccinated if you're likely to be visiting a place with an epidemic.
If there's another summer season like this one just gone, what would you expect people to do in regards for vaccination, kind of, I guess, jumping off that question?
Should I try? Yeah. So this is something that we normally don't have to deal with, because in temperate climates we really do have seasonality of influenza. But we certainly know that countries like Singapore and Hong Kong deal with this regularly. They have 2 peaks a year, or they have continuous influenza activity. And so there are now some studies going on to see whether, and they can't seem to get it right. I mean, you can vaccinate when there's 1 peak, and then you're not vaccinated for the second peak. So they're now doing studies about vaccinating twice a year. And I think we just stay tuned and see how those turn out.
Just in case there are any last questions, could I ask any offers on what's known about why some people get sicker than others? So we've talked a lot about the virus and future strategies. Anyone want to take that one up?
Well, maybe I could comment, Mike. We know that obese individuals are more susceptible to severe disease, as well as our Indigenous community. Mm-hmm. With the Indigenous, it may be that they have not evolved with the virus as we have, and their cytotoxic, thank you, their cytotoxic T cells that we were talking about, they do not have as good a range of the epitopes that can be recognised. And this is some more work of Catherine Kazetska's lab. They're very restricted in the responses that they can mount. So that could contribute to their severity, because they just don't have that type of immunity to fight the infection. But there's probably other reasons. There's a lot of co-infections and things that generally reduce the health of our Indigenous communities. It takes a lot of energy to fight an infection. You need to have good nutrition, you need to
have good energy stores, because the cells that are making your immune response take a lot of that energy when they're fighting disease. So if you're a bit undernourished or compromised through other diseases, it's a lot harder.
The only thing I would add is that there are now certain, genetic susceptibility markers that have been identified that are associated with severe influenza. And there are studies now looking at, now that the human genome has been sequenced, and we know much more about genetic markers of susceptibility. That's an area of intense research.
Yeah. Okay, well, looking at the clock, I think I should, unless there is an extra super duper burning question, but I suspect we're ready to perhaps brave the temperatures outside. So I'd like to thank all of our speakers here on the panel tonight. So, thanks all of you for coming. So, and thank you to the organisers, Rebecca and Finn and the team, Bex, for putting on this event. So thanks everybody. Have a safe trip home. Good night.
Thank you.